Okay. All right, welcome to lecture 10. We've pretty much gotten through the bulk of this course, all the stuff about fact and really what the first two exams are about. The rest of the content that I'm going to teach is very interesting, maybe on exams in small ways, but will mostly be useful for project stuff. So definitely be sure to watch these. They're really neat lectures here. So, okay, and they're shorter than most of the others. Okay, so this one's about transmissions. Okay, so what are transmissions? Transmission mechanisms are mechanisms kind of like this vice grip that are designed to increase forces or displacements and put them at different locations and different orientations. So they really do two things, okay? They amplify or attenuate a force or displacement, just like I said, like these vice grips, you clamp down with a small force, it gets a huge force out here, huge displacement here, a small displacement here. Here's, of course, the compliant version. We've seen this before. But the other thing is it changes the direction and type of input. So, for instance, in this one, the direction's going horizontal, but the output is now going down in a vertical direction. So transmissions can not only increase or decrease force and displacement, they can do so, they can change directions and at different locations and even different motion types. So this is a translation to translation, but we can even change rotations to translations or translations to screws or whatever. And those are the things transmissions do. So they're very useful because sometimes you need to buy an actuator that has certain capabilities. Maybe it's a rotary actuator or it's a linear actuator, but you need to turn it into something different. Say you only have a linear actuator that pushes straight, but you need to turn it into a rotation. You're going to need a transmission. Or say you have an actuator that has a huge load capacity, meaning it can push with a huge force, but it can only move with tiny displacements like a piezo. Well, then maybe you'd want to step it up so that you put the actuator here and push this way. It would push with a tiny little displacement, and this would really ramp up the displacement at a different place. But would of course, if you're going to ramp up displacement somewhere, you're always going to step down the force. But you might want to because you might have plenty of force but not enough displacement. Or stroke is what it's called on an actuator. And so you can really increase the stroke and ramp down the force or vice versa. And then it's just mechanisms. Oftentimes you have some input, some motor, and you want the output to be some gripper to turn into two motions that are like clamping together, so you can just transform motions into different motions or multiple motions at different places that clamp together like a gripper or something from a rotary motor. So transmissions are really useful. This is one of the most useful ones I've seen. That's why I'm showing you the example. So imagine this is just a big grounded body, and all this stuff in gray is a flexure, and this is like a piezo actuator. So if you put, you can see it kind of forms a double triangle. Here's one triangle, and then here's another triangle. So if you've got an actuator that can expand or contract, and you put it in here, just by virtue of this, first of all, it changes the expansion contraction along the horizontal direction to an output here in a vertical direction. But depending on the angle you have in these triangles, you can really ramp up with a double transmission and get, if this just contracts a tiny amount, this can move a huge amount up. If it contracts or it expands a tiny amount, it can move a huge amount down. And depending on the angle, you can tune that. If you have something that moves a lot, you can actually get this to move less, but with much more force. And it's kind of a double transmission packaging. So transmissions are really useful. Is the bottom line. Okay, so so let's look at that other example. This example here. But instead of a flexible hinge, we're going to just assume this whole thing is perfectly rigid, and that it rotates around this point with, say, like a revolute joint, but it has absolutely no friction. Okay, there's no friction anywhere. Nothing can deform. This is totally idealized. There's no source of energy dissipation anywhere. And say we push on this with a force input and it moves a certain displacement. Well, you can know that the work put in, which is F input times X input, equals the work or the energy that comes out. Okay, F output times X output. In a perfect world where all that it converts because of conservation of energy. If you divide those by time, then it's power. The power in is the same as the power out, right? Well, so in this idealized scenario, one, we can know that, well, first of all, two definitions here. Mechanical advantage is the output load divided by the input load. It's like how much you've, it's that ratio is what it is. That's the mechanical advantage, or MA. Geometric advantage is X output over X input. It's like you're caring more about displacements than loads, right? So anytime you're talking about loads, you're usually mechanical advantage. When you're talking about geometric advantage, you're talking about output or displacements, right? And in this idealized scenario, you can prove, I mean, if you just take this divided by that and take this divided by that, you can prove that the geometric advantage is the inverse of the mechanical advantage. Okay, they're flipped, right? And this is why, according to power arguments, you can't, if you're going to increase your displacement, if you're going to get a large geometric advantage, you're going to get you're going to decrease the mechanical advantage. Sorry, I think I pointed that wrong. But you see what I'm saying? If you increase the mechanical advantage, you're going to decrease the geometric advantage, and vice versa. So you can't ever increase the displacement and the force of an actuator. You're always going to have to sacrifice one or the other. Okay, and so, but this math here that's very simple can be confirmed with logic. This is an energy argument, but let's look at balancing torques, right? If you just take this force input and times it by B, that's the torque put on this. And that'll be the same as the torque output, which is the force output times A. And so if you take force output divided by force input, it's B over A. Okay? If you then, if you take balanced rotational angle, then what you get is, so thinking about this another way, of course you know the theta, the rotation of this body, times B is going to be X input. And so X input divided by B is theta. And of course, the whole body, as it's infinitely rigid, is going to rotate the same amount, so the same theta, which is also X output divided by A. So both of these equal the amount it rotates. And so from that, you can massage this, flip it around, and you get X output over X input is A over B, which is the inverse of this. So these literally equal, this equals the inverse of this, okay, which we just proved here through energy arguments, okay? Okay, but if the mechanism is compliant, meaning there's actually a compliant hinge here, or heaven forbid this actually deforms, and there's some strain energy that's absorbing some of the input energy, and maybe it's generating some friction, maybe you plastically deform it internally, or it rubs against something, or there's some sound or any form of dissipation, something like that, then this rule is no longer true. It's the input power or work is essentially equal to the output with all the extra stuff, strain energy, dissipation, friction, all these things, right? And so this no longer holds. But when you're designing compliant mechanisms, just or rigid mechanisms, even though compliant mechanisms, the whole point is they have strain energy, they deform to achieve the relative motions, it's still kind of valuable just to simplify things and ignore the strain energy, dissipation energy, and just use these equations to get in the ballpark, and then consider the stiffness later. Okay, so so with that, let me tell you some different approaches to design for transmissions. Okay, there is. One is kind of constraint-based design, where you just kind of, it's not really a systematic approach. Well, it's not systematic at all. It's essentially just learn a bunch of building blocks, be good at visualizing how things deform, be good at pattern recognition, and be creative, and slop building blocks together to get what you want. So it's an approach that basically takes a lot of experience. But here's how it would kind of work. So I know this is extremely unsatisfying, but this is something you should know about. Okay, so say you wanted some mechanism that fits in this design space. You want your input to be here, and you want your output to be here in these directions, and you want the geometric advantage to be, the output to be twice as large as the input. Okay, so the geometric advantage is 2. Well, say you just had these building blocks to work with. These are the most. These are some of the most common, and you can visualize how they move. You know this has an instant center where they intersect, so it gets a rotation. This gets rotations and translations, and this just gets a translation, right? So knowing this gets a pure rotation, then it gets a pure translation. Even though for large deformations, this arcs and the axis of rotation actually drifts on this, but let's just simplify things because it's tough to visualize all that. So let's just slop it in the design space. These different things where here's the rigid body up here attached to ground, and here's the two wires, and they intersect right there, so they'll rotate there. Here is just a wire to kind of couple these together, and then here's this parallel guide mechanism. And really, what you do to get this output is you make this twice as long as this input, so that you basically get the transmission just all from this building block. So you pull this, this is going to move twice as much in the other direction, and you just use this to couple them. And this is the translator to keep it nice and straight, to make sure it translates coming out. So this would be one way, some designer could kind of think and just put stuff together. So again, you just have to be familiar with building blocks. You have to be able to visualize things, be good at pattern recognition, and just be creative and slop it together, and you can get it. Okay, so not terribly satisfying way. Let me give you a better, more systematic way that just uses instant centers. You could see from that last approach, this guy was the most useful in actually getting the transmission. And this guy basically did everything. It changed the directions and did the transmission. The rest of this was just kind of moving the displacement over here. So the instant center approach, let's just use these instant centers, and we'll come up with a systematic way to do this. And this just works for 2 dimensions, and it's just a cute little approach that might prove useful for you. Okay, so here's how it works. So say you've got a planar, 2-dimensional design space. You want to design a mechanism here. The inputs here in some weird direction, the outputs here in some direction. Again, they can be anywhere they want on the boundary, pointing in any direction with any geometric advantage or mechanical advantage. Okay, so what you do is step 1, you draw lines that are perpendicular to these. Okay, so we see these blue lines we draw that are perpendicular to the input and output. Okay, then, and why we do this you'll see in a minute, but just trust me, I'm giving the systematic steps. So step 1, draw the blue lines. Okay, step 2, pick any point. Okay, sure. Step 3, pick a direction. Now, not all directions will work. But just pick a direction, and we'll keep going, and if it works, great. If it doesn't, pick a different point in a different direction, okay, is the rule of thumb. But, okay, so we pick this point, we pick a direction, and we draw a line perpendicular to that now. And at this point, whether you realize it or not, the design approach is pretty much done. Where these lines will intersect, you put instant centers. So this intersects there at there, this intersects there at there. That's instant center. And now you connect a rigid body that connects this point to that point that you chose, and you draw your wires. It doesn't matter if they go this direction or this direction, this direction or this direction. Just draw your wires, and it doesn't matter if they, where they intersect or whatever. But you'll know now that when you push this stage will rotate around that point, and you can see here the direction you pick does go in the right direction. If they had gone down this way, I would have recommended point the opposite direction. So if as you go through this process, you pick a direction that doesn't work, just flip the direction and try that, and it's likely to work. Okay. Okay, and then the other one's already set in stone too. You connect that point to the output, make this rigid, and you could do wires in either direction. In this case, you'd have to keep it in the box. In this case, you wouldn't want to do it the other direction because it'll collide with the other one. So you kind of do it like this, and you've got a design that when you push this, it rotates around there, pushes that up, that pushes this, and it kind of rotates there and pushes that. And then what you do is you define the distances between the center, the instant center and the input, the instant center and the intermediate body and the instant center there, the instant center there, and there. Okay? And you get the output. Okay, so so this is so we have these amounts A, B, C, and D, and now we need to understand the relationship. Okay, this is by the way not this is kind of a tangent. This breaks away from the systematic steps, so I'll get back to it and review them. So if you imagine, this body, whatever it rotates, say delta theta 1, If you times it by b, this distance, that will be the intermediate distance, right? That's the definition of that. And the input displacement equals a times the same angle, because this is a rigid body, it's going to all rotate the same. At every point it'll rotate the same, right? Okay, and so now you take the derivative of these intermediate to input and you get b over a, and the theta cancels, okay? Let's look at a different relationship now. D times theta 2, it's a different rotation amount. This one won't necessarily rotate the same as this, but whatever it rotates, every point on it will rotate the same amount. So you times that by d and you get the output, and you times that same thing by c and you get this intermediate displacement. Divide the output by the intermediate one, these cancel, you get d over c. Now look at this last one, so it's intermediate over input, and this one's output over intermediate. So if you times those two together, take d divided by c and times it by b divided by a, the intermediate will cancel and you'll get output, over input, and you get this times this. And so, and you look at it, you don't really, at this point, you can't really tune D or A, but you certainly can tune B and C. So you could drag this point and slide it along here and change the geometry so you can change B and C so that their ratio gets, when it's times by D and A, whatever that is, gets the output ratio you want, okay? So again, here's the whole systematic step, okay? Let me just do this again here real quick, okay? So, okay, here's what they asked for. Draw perpendicular lines, pick a point, pick a direction, draw a perpendicular line to there, draw the instance centers. Now draw these things, connect them, and label these things. Okay, identify what things you can't change, what things you can change what you can change to get the transmission you want, and you're good. Okay, if the direction you picked in this step didn't work, flip it and see if it works. Okay, all right, so let's try it for this. Let's do it in another example. Say this is 30 degrees and you want some input. This is 30 degrees and you want some output, and they're going in different directions. And you have a geometric advantage of 4. So that means if you put 1 in here, you'll get 4 out here, okay, displacement-wise. Okay, so let's do it. Draw perpendicular lines. These are perpendicular to the arrows. Okay, pick a point, pick a direction. Okay, draw a perpendicular line, and now you're kind of set in stone. You draw the instance centers. Okay, connect them. Put the wires in directions that aren't going to collide with anything or go outside of the box. Okay, do the same thing on the other side. And now recognize the distances between the instance centers, the inputs, and the intermediate bodies. It's A, B, C, and D. Write out the geometric advantage that we proved in that last example. It's going to be the same for every example, right? A and D we can't change. They're just whatever they are. In this case, they're both equal, so A and D would actually cancel. And so now what you would do, and they don't need to be, they could be different, and whatever they are, you just take note of that, right? And then whatever you do is but in this case they're equal, so they cancel. So B and C needs to equal 4. And so what you can do is just move C so that it's 1, so it's 4 times less than B. So whatever B is, take its length and divide it by 4 and make that C's length, and you've got your geometric advantage of 4. Now again, if D and A hadn't been the same length, whatever they were, say D divided by A was 2 instead of 1, well, then B divided by C better be 2, right? So the final geometric advantage can be 4. But in this case, they were equal, so that's the ratio. Let's see if it works. You cat it. You see that? Make them all the grounds common, and then push on it, and you can beautifully see here, this is just SOLIDWORKS, for every 1 distance you push here, you get 4 distances out here. Okay? Okay, so that's a cool little way to design things, to change, first of all, to design planar things. It's limited to planar. It's also limited to inputs and outputs that are translations at different locations. And it's just going to be kind of approximate, right? Because it assumes all kinds of ideal things. You're not going to get exact things, but it'll get you in the ballpark pretty nicely, okay? And it's a clever little approach, okay? But all your designs will look like a bunch of, bodies with instance centers and stuff, okay? But that's okay, right? Okay, so now let's do the screw-based fact approach. So I'm going to show you how fact can be used, the principles I taught you with fact, how they can get transmissions. Okay? So there's many ways you could use fact to design mechanisms of transmissions, but one of the absolute keys I realized as a PhD student when I was trying to look for applications for screws. Okay, so you might recall these mechanisms. Here you get a rotation, here you get a translation, and here you get a screw, right? These are familiar mechanisms to you. Well, back in the day, I was trying to find, what's an application for a screw? When does anyone ever need to achieve a translation with a coupled rotation? Yeah, so I mean, there are applications out there, but none were terribly compelling that I found while I was a PhD student. But then I realized, my goodness, screws are the key to transmission, and transmissions have tons of applications. There's lots of applications for transmissions, and they can enable all sorts of crazy transmissions that no one could ever intuit and come up with. And let me show you how. So if instead of grounding this stage and allowing this to translate and rotate with a coupled pitch, what if you, what if you put something on top and bottom here and sandwich these together? So now, and you still ground this one, you still ground this one, this outer one, but now this one is not allowed to do anything but rotate, and this one's not allowed to do anything but translate because of these bearings. So check it out, right? These bearings only allow rotation, these bearings only allow a translation. So if we sandwich this and allow this to only rotate and this to only translate, then it would be reasonable, say we join our grounds together, it would be reasonable to assume we could transform a rotation to the translation according to the pitch of that screw. Okay, so you can see this better if you get rid of the ground, but say it's still there. Okay, and we zoom in here and show it side view, you can see how beautifully this is working here. One bearing set guides the rotation, one bearing set guides the translation, and then this guy, the screw, gets the whole transmission and sets what the geometric advantage would be between the different motions. Now, it's important to recognize that the pitch will be the pitch of the screw will be the transmission ratio, essentially, only for ideal constraint assumptions. So if these constraints were infinitely stiff along their axis, but infinitely compliant in all other directions, as we've been assuming in the fact library, then yes, whatever the pitch of this screw is will be the transmission ratio. If the pitch is 1 or 2 centimeters per 1 degree or something, then that means if I rotate this 1 degree, this will move 2 centimeters. And if I grab that and move it 2 centimeters, this will rotate 1 degree. So it'll be back drivable, and the pitch will be the perfect transmission. However, add reality to the mix and don't have these constraints be ideal and infinitely stiff along their axes, etc. And instead allow them to compress, allow them to exhibit the elastomechanics they actually do. And what you actually find is it's only approximate. The transmission ratio is not the pitch, it's only approximate. And it's actually not back drivable, interestingly enough. Like, if you rotated this some degrees, say 1 degree, and this one went out 2 centimeters, if you move this 2 centimeters, this is not going to do 1 degree. It's going to be different. So it's not, it depends on what the input is and what the output is you define that determines the transmission. And it's not as clean as just the pitch of the screw when you add the realities of elastomechanics. But I will lecture on that at the end of this lecture, and we'll talk about how we can find that and calculate it, actually. But as a good rule of thumb, if you're trying to transform a rotation into a translation about the same axis with a certain transmission ratio, do it this way and start off by tuning the pitch of that screw to be the transmission ratio you want. Okay, and it'll start you in the ballpark. Then you can optimize it to get exactly what you want. Okay, so you can use this same trick to turn translations into translations going in the same or opposite direction, different amounts. You can use this trick to turn rotations to rotations, same or opposite directions, different amounts. And you can use it to turn screws to screws with different directions and different pitches at different amounts. Okay? And you could obviously turn this from translation to rotations, translation to screws, screws to rotations, and screws to translations. Okay? The only problem is you're thinking, well, this only works as long as these things are all along the same axis. Well, that's actually not true. Oh, by the way, here's the side view of this, showing how clean everything is. Okay? So remember this flexure that essentially achieved a screw motion. We've added some extra constraints. You can see here's the original, these angled ones, and then here's the side crossbar. We added another side crossbar on the other side just to make it more symmetric. You'll remember when we had the flexure kits, we built this with 5 constraints. Here we've added a 6 angled constraint on the other side that's angled the same way, same distance, so we get a nice screw that's a little more symmetric, right? So we have our screw. Okay, what could this be used for? Well, again, it's great for transmissions. If you actually don't ground this, but attach it to bearings that only guide a translation, ground these. So now, instead of grounding this, you allow this to translate. And then you add another set of bearings that goes from the ground to here that only allows this to rotate. You can see those guys constrained to only rotate. Then now you can turn your rotation about this axis into a translation off axis. Okay, so the translation can go in a very different direction, or be at a different place than the rotation. Okay, of course translations don't have locations, but watch this. If you stack this on this that's slightly shorter, a similar thing, you can get rotations that are not along the same axis. In this case, they're parallel though, but they're not along the same axis, and they can be in different directions and different amounts using this trick. So hopefully you can see how screws can be the absolute key to being the heart of transmission mechanisms to transform any motion, any other motion at any location with any transmission ratio in very complex ways that no one could do without this theory. So let me to show you how complex this could be. Okay, my friend, this is one of the last things I did, my PhD, is a friend challenged me to say, okay, here's your design space. Okay, and here's your output stage, and I want 2 input stages, and I want this to be a microscopy stage, so that when you high precision stage that you drive with your hand, right? So hands are very not repeatable, as you know. Like what's the most repeatable number of degrees you can rotate? And how repeatable is that? It's not great, right? But if you could make flexures, attach all these within this box, and you could make it so every time I rotated this a degree, this output stage moves 50 microns, say, or whatever, right, you want, to step down, to dramatically increase the resolution repeatability of your hand, and make it so it moves tiny amounts. And then say you grab this one with your other hand, so you're grabbing it like this, right? You're like rotating. You grab this one like this, and you're rotating. And this one can translate this one with the same thing. For every degree here, 50 microns or whatever you pick, right? So and then the other thing is, he said, that can you decouple these so when I rotate this, it doesn't affect this one, and when I rotate this, it doesn't affect this one. So it'd be bad if when you rotate this one also rotated, which would usually be the case since this is going to be all one monolithic structure, all connected, deforming. So he not only said, I want you to have 2 inputs that you can independently rotate and be decoupled, but I want them to both link to independent translations of an output stage that's dramatically stepped down. So you can imagine if you have this, you could with your hands just be rotating this and moving this around tiny amounts under a microscope with high resolution. So it could transform just a structure that uses the coarse resolution of your hands to position something. And if they're decoupled, like, you can independently set X and independently set Y without affecting each other. Okay, well, how did we do this? Or how did, so what I did was I said, okay, let's start with the transmission. Okay, first of all, I noticed, okay, we're turning a rotation over here into a translation there, and we're turning a rotation here into a translation there. Okay, and it's 2 degrees of freedom. So let's let's do a system that achieves 2 screws that are going to align with those. Okay, so what I said is, let's first of all visualize grounding it here, and let's get